Swayam Prabha. Digital India. Educated India.
For example, let's take this simple case. So we have additional triangle here. Let's say I want to remove this triangle. So what I can do this is that I can collapse its edge and make it a single edge here. So essentially I'll be retaining only this triangle and a triangle that is here. So in this particular case, what they have done is that so they had these two triangles which were vertically opposite to each other, depending on this property that they are sharing a common edge, and we have these two edges that can be collapsed. So what they do is they convert this into a single point to which they collapse, and both these edges are combined. So this edge and this edge gets combined into a single edge. Similarly, this edge and this edge gets combined into a single edge. So this way you can essentially reduce the number of triangles. So now earlier you had one, two, three triangles on the top section, but now when you have collapsed, you are essentially moving the vertex V1 to the vertex V2 and collapsing all the edges across those vertices. So essentially the top triangle and the bottom triangle has collapsed. So if I want to collapse in this particular case, so what I can do is I'll take this vertex, I'll take this vertex and join them both to create a single edge. And I'll remove this edge and this edge. Is this clear? Any doubts? I hope this is clear to everyone. If it is not, please let me know. I will just go through it again. So this is basically you can simply collapse edges falling on a given set of vertices and reduce the number of triangles. This is a straightforward operation. So IGL performs this and it does so basically you can specify to what extent you want to decimate it to. So you specify that you want only 1,000 phase or uh, what, 1,000 phase mesh. So you can simply pass on the current set of vertices and faces. Yeah. Yeah, so you have a doubt? Okay. Okay. I think your microphone was also or something. Anyways, so you can simply pass on the number of triangles you want in the decimated mesh, and IGL will perform something like edge collapse in the background and will do this repeatedly till the time the number of faces reduced to 1,000. So now what you can do is you can see that this mesh is a simpler version of the earlier mesh that we had seen. There is some amount of loss of information. However, overall structure still resembles to Bunny to a great extent. However, this is a decimated mesh. Furthermore, notice that now the mesh looks a lot more regular as well. So if you notice the facial structure, earlier there was a lot of information in the face, but now it has been lost. So that means a lot of decimation has taken place in this particular region, in the face region, or in the region around the legs of the bunny. So now it has become much more smoother, and now the number of faces are also less. However, if you notice, let's also plot it with the angles that we have now obtained. Now you see that these are the angles. Now the angles are also far more uniform than before. The number of darker triangles has reduced tremendously, and it has become a little bit more regular for the mesh. Similarly, what you can do is you can perform a subdivision. So right now we are going from a low resolution mesh from a high resolution mesh to a low resolution mesh. But you can go the other way around as well. You can go from a low resolution mesh to high resolution mesh. If you guys want to try it out, you can quickly try it out this function as well. Also note that I'm ignoring the some of the parameters, some of the variables that are being returned by this function. I'm only focusing on the new faces and new vertices. So you might want to take a note of that. You can quickly try it out and let me know in case you face some troubles. So all you need to do is call igl.decimate with v comma f comma number of faces that you want, and it will return you some parameter, some other variables along with the v and the f that are newly formed. So now we are going to use this decimated mesh to perform a mesh division and go to a high resolution mesh and see what kind of information is revealed. So coarse mesh is also called a mesh cage. So we can go for different kinds of subdivisions. So essentially what subdivision is, so right now we are collapsing edges, right? We are reducing the number of triangles. So we are going from a pentagon, so to say. We have, all right. So let's say you have this simple a decimated mesh which looks like this. Now you want to increase the number of triangles. So what you would want is that at different spots you increase the number of triangles, and there are different ways to do that. So right now you can basically split it like this. Like I picked an edge, I took the opposite edge and took the midpoint of it and joined it. So this is one simple geometric criteria that I can pick. There are different other criteria as well. So you can even divide it using a centroid. So let's say the centroid is somewhere here. So you pick a centroid and you join them to the vertices. Now you have obtained three new triangles. So this operation can be repeated across a mesh to give you a more coarser mesh. Sorry, a finer mesh. So these are the different operations that you can perform. So you can perform a simple upsampling. So upsampling basically uses the midpoint of the edges, just like I had shown you in the first figure here. So this is using a midpoint criteria. This is using barycentric center. So are you guys aware of the term barycenter? I guess just be is, and some of you guys who are already familiar with geometry might be. But essentially, a barycenter is nothing but the centroid of a triangle. Barycentric coordinates basically mean that with respect to every vertex, you do a partition of unity and you use that partition of unity to figure out a point in the inside of a triangle as a linear combination of the points that are available to you. So any point, say you have a point, so let's say you have a triangle and you have a point P here and you have three vertices V1, V2, V3. So what barycentric coordinates say is that this point P is essentially some partition of unity of the vertices that are already present. So this point P can be written as PV1 plus W2 V2 plus W3 V3. So this is a barycentric coordinate because it is essentially now W1 plus W2 plus W3 is essentially 1. So you say essentially that if you have a unit area triangle, so P can be represented as a linear combination of these vertices, where W1 is essentially the ratios of the triangles that will be formed by the opposite edge. So W1 could be calculated with this area divided by the complete area. So W1 is essentially the ratios of the area of smaller triangles divided by the ratio of the total area. So this is how you can calculate W1, W2, W3, and similarly you can express any point inside as the barycentric coordinate. via its barycentric coordinate. I hope this point is clear. If it's not, just let me know. We are not going deep into the maths. I just want you to know that you can perform such upsampling of the meshes using different ways. So each of these upsampling further changes the mesh properties. So especially I'm focusing on the internal angles because it would help you visualize what kind of changes are taking place within triangles when you try to visualize it. So for each of these upsample, loop, and false barycentric subdivision, you are also going to calculate the internal angle. So when you perform the upsample, I took in the decimated vertices and faces, and it returned me a new set of vertices and faces. Now I'll take this set of vertices and faces and compute the new internal angles. And then we are going to look at what kind of shading each of these different kinds of subdivisions give. So for example, this is a basic subdivision that we have performed right now. So this is a simple mesh subdivision. The colors are just the default colors right now. I'm not using any other colors. So I took the decimated mesh and I have converted into, oh sorry, I took the, yeah, decimated mesh and upsampled it to have a large number of triangles. And now if you see, we have recovered some face information as well, which was earlier missing. So, sorry, this was the original one. Now we look at the decimated one. So there are some more facial structures now that are visible. It has become a little bit more sharper. And these are the angles for different triangles. So there are some sections of uniformity and some sections that are vary. Now this is the another one. So the loop essentially ensures that there is some C1 continuity in the surface as well. So if you look at it, you'll see that there are some contours that are here. These contours occur due to the loop structure that is being applied. So you'll notice that there are some loops that are occurring inside the mesh. Now, if you compare it with this one, there are no loops as such. The contours are only visible in this particular section, but there are no specific loops that are visible. But if you look at this one, you can see that there are waves going on of triangle, and you can see that these waves are visible. So essentially, this happens because of another constraint which is put on the continuity of the mesh. Now, if you look at the barycentric one, you can look that there are some centers that have been formed. So all these new centers are essentially the barycenters. So based on these centers, you get new sets of triangles. And the angles are also different now, as you can see. Perhaps I should turn off the lighting as well. Shading. Yeah, so I hope this part is clear. Any doubts in this? You guys want to quickly try it out? You can do so. We'll just so now I've disabled the wireframe so that we can look at the structure. So if you look at this, this has some sharp edges, this mesh subdivision. However, if you look at this one, the one which is done with loops, is far more smoother because of the kind of constraints it is ensuring. And then comes this one. This has a different structure because of the berry centers it is creating. I hope all of this is clear to you. If it's not, just let me know. I'll repeat. So this is the code. If you want to quickly try it out, I shall copy paste it. If you want to. Okay, I'm not sure the chat has preserved the new lines. Anyways, just write it out quickly and let me know once you are done in the chat. Just write a +1 if you are done with this part as well. Also, let me know if I'm going too fast or too slow. Uh, yeah. Just write a +1 once you are done. Any doubts? So, Mom, Gaurav, Vignesh, Darshil, Monica.
Participants, I hope you're following. Please respond, otherwise it becomes difficult.
Yes, yes, we are following. Sir, one thing, if you can share the Python file, we'll run the code. Like if it get to type it now, maybe there we are waste of time.
See, I would want you to type it out. I'm not in a rush, and these are small exercises. Why I'm
Okay,
asking you to do it is so that you should be familiar with it. You can
sure.
obviously do that as well. You can say, I could have provided you with this Jupyter notebook directly too. But then, in case you run into some errors, we can discuss those errors side by side. Okay, Darshil is done. Anyone else who is done? Okay. Anyone who has any doubts? I hope plotting is also clear. All you need to do is pass in three parameters, angles to view the. So we are essentially using the angles as colors in this particular case. Gaurav, any doubts?
No, no.
Okay. Um, Shall we move forward or are you guys trying it out? Anyone who has any doubts before this part in the above sections in decimation or anything? Okay. Fine. Yes.
So, am I audible?
Yeah, yeah, yeah.
Hi, Madhu. I missed the starting 10 minutes of the class from 2 p.m. But I had a doubt, like the mesh files that were created. So I was trying to create one mesh file myself. So, like, if I have, like, let's say, a set of XY coordinates or like a point cloud file, and there are holes in the file. So, like, I applied the margin cubes algorithm and
Hmm.
tried to create a mesh file out of it, but there are holes in it. So, like, how do you would you suggest to fill the
Yeah,
holes and
see,
like?
you can do it both programmatically and you can even use MeshLab for that. So in the starting session, I had shown that you can use MeshLab and there's a
Okay,
hole filling tool in it. So you go to MeshLab and
okay, okay,
directly, I'll just share the
okay.
screen. Okay, Vignesh is facing an error. IGL not defined. Vignesh, have you installed it via Conda?
Yes, yes, I have installed it, and it was working till the previous thing. But when I like pasted the code, it is not. It is giving me this error.
So you're saying till decimation it worked?
No, not till decimation. I didn't do decimation. I directly jumped over to upsampling,
Okay.
and instead of v underscore f underscore, I directly input v and f.
Okay.
So,
Yes.
and suddenly IGL not defined.
Okay, maybe your kernel has restarted. B and F already have a lot of vertices and faces. So if you try to subdivide it further, maybe you'll run out of memory and the kernel will get killed. So I would
Okay,
advise you to first perform decimation and then do the subdivision so that you can check it out. That is why I
sure.
also used the decimation first. So there's a
Okay.
possibility that your kernel got killed and now you might have to do the imports once again.
Okay.
Yeah, so Atul, so you see this option here, fill hole. When you load a mesh with holes, you can directly use this tool to fill the holes. So it will show you a set of holes and you can fill them all directly. Otherwise, they are
So
programmatical.
will it be able to fill like if there is like a tunnel sort of a thing, which is like
Yeah,
connected, but it's like a
yeah,
tunnel.
yeah. I'll show you. So actually, I think you missed that part. But
Okay.
we had earlier done hole filling in a bunny mesh. So the bunny mesh
Okay.
is a hollow mesh, and there are several holes. So it will basically the algorithm is tuned such that it covers the surface, and through that it performs some energy minimization and fills the hole in those spots.
All right. Okay.
So it will do that surface completion for you. You can try it out quickly if you want to. The bunny.obj has holes in it, so you can quickly load it up in MeshLab and
Yeah.
check with the
Okay.
hole fill tool.
Okay. Okay.
Okay. So let's move forward now. Vignesh, just let me know if you still face problems in it. Just first try performing decimation and then do the subdivision. I think it should work fine. If IGL was working fine. Yeah. So once
Hello,
you're
sir.
done with yeah.
Can can you again tell me what is happening in bicentric subdivision?
Okay. So it's called barycentric. So what you essentially do is you compute the centroid of a triangle. So you have a triangle, right? ABC. The centroid is essentially the you can do the centroid computation. It's nothing but ABC by 3 in two terms. So this is a centroid, right? So what happens in barycentric subdivision is that you take a face, you find its centroid, let's say it's point P. Now what you do is for all the other vertices, you join them to the vertex P. So now essentially you have obtained three new triangles from a single triangle earlier. So this is a barycentric subdivision essentially, in simple terms. Other way that
Okay.
I had shown earlier was that what you can do is you can take a triangle, say ABC. You can take each vertex and join it to the midpoint of the opposite end. So now you have obtained two new triangles. You can either do it this way or you could have joined C to the midpoint of the other side and created two new triangles, or similarly here. So there are three possible ways of getting new triangles, or you could use all of them to get six new triangles. I hope this is clear, Darshan.
Yes, yes, sir.
Any other doubts? So once you perform decimation, another thing is triangulation. So we are not going to discuss this in much detail. I think a session has already been done on triangulation in detail. We're only going to look at the SciPy library and how it enables you to perform Delaunay triangulation. So all you need to do is SciPy.spatial has a function for Delaunay. All you need to do is take a set of points and pass it on, and it will perform the Delaunay triangulation, and it will return you the simplest for it. So like I these are these are vertices that have been passed. So this one is vertex 0, this is vertex 1, this is vertex 2, and this is vertex 3. So if you look at the simplices, it has returned me two triangles from these set of points, and these are the vertices of those triangles 2, 3, 0. So this vertex, and the first vertex form the first triangle, and 3, 1, 0. This vertex 1, 1, 0, 1, and 0, 0 form the second triangle. So this performs a Delaunay triangulation for you internally. There are some you can do this from scratch as well if you want to. However, this is a much more efficient way to do it. So I would suggest you to do the library. It has already been optimized. And similarly, you can perform for the three. So this is the plot. If you try to plot these points now after triangulation, these are the two triangles that have been obtained. So Matplotlib has a something called as try-plot. So using that, you can actually take the set of points and use the simplices to directly plot the triangulated points. The first plot is for plotting the triangles, and the second plot is basically for scatter plot of the points themselves. So you can use this to plot the triangulation in 2D, and similarly you can do it in 3D as well. However, in 3D, there's one more thing you need to take care of. You'll be performing the Delaunay triangulation for the UV or the 2D points, and then you'll be using them along with the third 3D coordinate to create a 3D surface. And Matplotlib has a function called as a plot try-surf. So using this, you can directly use the simplices and the points to plot the 3D surface. I hope this is clear. So in this case, you obtain a 3D pyramid using the try-surf. Any doubts in this one? This is straightforward. I think you can look it up later on as well if you want to, or you can quickly try it out right now. Do note that there's a transpose operation here when after I concatenate UV together to reshape it appropriately. So you can use this to directly plot it. You can just check it out later on. So these are this projection 3D is needed for 3D plots in Matplotlib. So now we are going to introduce a new library called as PyGal Mesh. So there is a library called CGal. Hello, am I audible?
Yes, sir.
Okay. CGal. Check on this. Okay, I see that. Okay, there is some issue with the network, I guess. Anyway, so there's a library called as CGal. PyCgal is essentially a Python wrapper around that library. So what you can do is, in the case of irregular meshes, you can remesh a surface with some added constraints to it. So for example, in this one, I've added some constraint like facet distance, facet angle minimum that can be allowed, then the max edge size of the feature edges. And if I load this again, let's take a look at this one. So if you want to install, you can install it using pip. You can install PyCgal mesh. I don't know why the site is not loading. Okay, fine. So this is a computational geometry library. This is essentially a C++ library, but it has wrappers around with Python as well. So we are using PyCgal. Anyways. So you can simply use PyCgal and also install Mesh.io when you are at it, so as to write the meshes back. So PyCgal mesh can be used to load a mesh and perform a remesh of surface. So when you do that operation, what you will notice is that this was the original mesh that we had, v comma f, and v2 comma f2 is the remesh bunny object. So I'll just copy this so that you can quickly try this out. I've shared this function call so you can directly use this. Then use mesh.io to write the mesh and then reload it once again using IGL. If I'm going too fast, let me know. However, you should by now be a little bit more familiar with the syntax and semantics. So just quickly do till here and plot the new vertices and faces. You'll notice that there is a slight difference in the remesh surface. So what remesh has essentially done is that now if you print the mesh statistics as we had seen earlier, this mesh is going to be a lot more regular than the previous one. Now the number of irregular vertices is only 9% as compared to the previous one. So previously we had nearly 34% irregular vertices, but after remeshing, so it has essentially played around using these constraints and created a more regular mesh. So these are some heuristics based on top of which you can decide what kind of constraints you would want to apply. I won't go into the mathematics of those. Those things get a little bit more dense, but you can read it up at your own pace. How these each of these uh, attribute is coming from. So Delaunay ball is basically the same Delaunay triangulation that we talked about earlier. So in that you draw Delaunay balls around every vertex set, and so that is this is the property of the Delaunay ball you're drawing. So that is the maximum radius with which you populate a sphere or a circle around your point while doing Delaunay triangulation. So this mesh comes out to be a lot more regular mesh. Now we are going to play around with TEDGen and then we are going to close it with one more exercise that we'll be performing. So we are now going to look at tetrahedralization. So up till now we have looked at surface meshes and how you can manipulate them. You can perform subdivision, you can perform decimation, you can convert a irregular mesh to a regular mesh, and you can do a Delaunay triangulation to obtain a surface mesh from a given set of points. And yeah, so we have covered most of the things with the surfaces. Now we are going to look into tetrahedralization. Any doubts till now? Do you want me to pause and you want to try this remeshing as well?